This is the screencast for section 1.3, example 9. We're going to analyze the absolute value of x function. First of all, I want to do as much analysis as I can without looking at the graph. I know what the absolute value of x looks like, so I'm going to try and use my frame of reference, my brain, to help me with my analysis. The domain. Well, I know that I can plug in any number to the absolute value of x and still take the absolute value of it. So my domain is going to be all real numbers. There are no discontinuities in the absolute value of x. The range. The absolute value of x goes as low as the origin, 0, 0, and then goes all the way up to positive infinity. So we do count 0. The absolute value of 0 is 0, so we do have the output 0, so we put brackets next to that. It goes all the way up to infinity, which actually this already then helps me with the boundedness. I can see that the function will be bounded below but not bounded above, so boundedness is bounded below. When we were talking about the domain, that actually helped us with our discontinuities. I can draw the entire absolute value function without picking up my pencil, so there are no discontinuities. There is that extrema though. The range only goes as low as 0. 0, 0 is the absolute min of the absolute value function. Now I also know that the absolute value function from one of our previous examples is kind of like a piecewise function. On the left it's decreasing, like the line y equals negative x, and on the right it's increasing, like the line y equals positive x. So I'm going to say that absolute value of x has some increasing and some decreasing parts. It is decreasing from negative infinity to 0. So to the left of the y-axis, and then for the x values 0 out to positive infinity, the absolute value of x is increasing. That means there's also even symmetry. We've explored this earlier in earlier examples. If I plug in negative x, the absolute value of any negative number is a positive number, so I end up with the same as the original function when I plug in negative x and positive x. There are no asymptotes on the absolute value function. Therefore, that is the conclusion of my analysis of the absolute value of x function. The now try problem for example 9 has nothing to do with example 9. I'm going to do it anyway. I just don't get why the book connected these two problems. Whatever. So we're going to go back and talk about pizzas. Pepperoni pizza. For a statistics project, a student counted... Whew, there was an answer there. I hope you didn't notice that. For a statistics project, a student counted the number of pepperoni slices on pizza of various sizes at a local pizzeria, compiling the following table. So we've got the radius of the pizzas and the pepperoni count. Explain why the pepperoni count, p, ought to be proportional to the square of the radius, r. Well, because the bigger the pizza, the more pepperoni you can fit on it. Part B, assuming that p equals k times r squared, use the data pair 4, 12 to find the value of k. Well, we've done this in section 1.1, so I'll repeat the process. I'm going to plug in 12 for my output value, which they're calling p. I'm solving for k, and I'm going to plug in 4 for the input value, r. So k times 16 equals 12. Divide both sides by 16. And my k value is going to be 3/4. So it should be y equals 3/4 x squared, except we're not using y and x. We're using p and r. Question C asks, does this algebraic model fit the rest of the data as well? Well, that means I'm going to have to use some lists. So stat, edit. In L1, I'm going to put the radius of each of the pizzas. In L2, pepperoni counts. I'm going to plot that data. Second stat plot. Plot number 1 is already graphing L1 and L2. L1 is my x values, L2 is my y values. Then in y equals, I need to put the equation I came up with. Y, or the output, equals 3/4 x squared. And then I'm going to hit zoom 9 and see what I got. Look at that. Fits just perfectly. So in conclusion, does the algebraic model fit the rest of the data well? Yes, it does.